So this video is going to show you how to sketch trig functions. So we're going to do one with sine, one with cosine, and one with tan. And it's functions where the parameters have been changed a bit. So it's not just plain old sine, cos, and tan. So the easiest thing to do is probably start off by identifying all of these different parameters. So we'll start with the amplitude. The amplitude, if you remember, is always found by looking at the number that sits in front of the function. So in this case, our amplitude is 2. Next, we usually identify our frequency. So if you remember, frequency is how many cycles occur in 2 pi, and you can find that number by looking right in front of the variable. So in this case, our frequency is 3. And so then the period can be found by dividing 2 pi by whatever the frequency is. So in this case, we get 2 pi over 3. Sometimes that'll be a fraction that we can reduce, but in this case, 2/3 pi is as simple as it gets. And then we identify any shifts that are going to either cause the graph to move up or down or left or right. So in this case, because this +1 is only coming at the end and it's not in parentheses, we know that that's a vertical shift. I'll just abbreviate that as VS. And since it's positive, that means the graph would be shifted up 1 unit. Okay, so now we're ready to set up our axes. So since we're only sketching one cycle, we're going to take our period and mark that right at the end because that's the number where that first cycle is going to stop. And then we sort of divvy up the axes into 4 pieces. So if we cut 2/3 pi in half, we get 1/3 pi, or pi over 3. If you cut pi over 3 in half, you should get pi over 6, or 1/6 pi. And to get the third number, this one can be tricky. You're really adding 1/6 pi and 1/3 pi. If you have to do that in your calculator, you can. You should get a half, which we would write usually as pi over 2, or you could write 1 pi over 2. Okay, so that's our x-axis. So for our y-axis, usually if I had an amplitude of 2, like I do here, that would mean my sine curve would be going up to 2 and down to -2. However, because of this vertical shift, that's going to change a little bit. So what I'll usually do with the vertical shift is I'll identify my maximum, my minimum, and also where the middle of the graph will be, because that can be kind of a helpful guide as we're plotting our points. So since the typical maximum of this graph would have been 2, and we're shifted up 1, it's now going to be 3. Our minimum goes from being -2 up to -1, so it's no longer symmetric about the x-axis. And the middle would occur right smack in between those values at 1. So I'm going to label all of those on my axis. So if this is 3, this is probably 1, and -1. What I also do at my middle, I really call this my midline. I actually sketch in a horizontal line. It's helpful because you're so used to sketching on the x-axis, it's nice to have that horizontal line to use to balance out your points. So I'm ready now to start plotting. Remember that this is sine, which means I start in the middle. I always start at my midline. So I'm going to plot right on 1, then I'll go up to 3. Then I come back down to my middle and down to my minimum, and then back up. Remember, when you connect your points, you're doing it smoothly. You don't want jagged points or jagged edges on a trigonometric graph. So you get something that looks like that. So that's an example of graphing a transformed sine function. Now we'll take a look at a cosine function. So here is y equals -cos 2 and then parentheses x minus pi over 4. So probably the first thing that you're noticing is this negative sign, and we want to make sure that we know how to deal with that. So if you remember back from geometry, when you negate a function like that or a function's values, it causes it to flip over the x-axis. So where a normal cosine function might have this general shape, when we flip it, it's now going to be upside down. So it's kind of going to look like an upside down parabola almost. So we want to keep that in mind when we're sketching that we're not doing the normal points for a cosine curve. We're doing them backwards. Otherwise, we can go ahead and identify everything that we did earlier. So our amplitude in this case, be careful here not to write -1. Amplitude is a distance, so it can't be negative. We would just say 1 since there's no other number sitting in front of cos. Frequency in this case is 2. So there will be 2 full cosine curves in 2 pi. Our period then is 2 pi divided by 2, which this time does simplify down to just plain old pi. And then again, we're looking for shifts. Since this minus pi over 4 is inside parentheses, that makes it a horizontal shift. And if you remember the way the directions work, if it's negative, that means it's going to the right. It's sort of the opposite of what you'd think. And there's no vertical shift because there's nothing at the end. So the way we normally would deal with a horizontal shift, you don't have to do it this way, but I do think it's easier, is sort of ignoring this until the end. So graph your negative cosine 2x, and then we can shift all of our points and actually come up with a second graph that would be our final answer. So that's what we're going to do. So why don't we go ahead and set up our axes? So yet again, we take our period, put that at the end, and then just start chopping that into pieces. So this would be pi over 2, this would be pi over 4, and again, remember that trick of adding these two values together. If you add a fourth and a half, you would get 3/4, or 3 pi over 4 in this case. Okay, for our vertical axis, we just have an amplitude of 1, and there's no vertical shift, so I'm just marking 1 and -1. Try the best you can to make those ones be the same distance away from the x-axis. Okay, so now I'm going to go ahead and start plotting. Remember, I'm plotting just a negative cosine. I'm not doing any shifting just yet. So I'm starting at the bottom and slowly coming up to the maximum. And then I'm smoothly connecting the dots to the best of my ability. Okay, so that is not my final answer. So now usually what I'll do is I'll use a different color pen. So if you're able to do that, that's always a good idea. And all of my points are moving pi over 4 right. Now notice the first increment on your x-axis is pi over 4. So that's exactly that distance for all of your points is really just one increment on your x-axis. So here, these black points on my screen are the new points. So if you connect those, you kind of see how it's been shifted. You can do that last point if you want. You don't have to. Sometimes we even do it with a dotted line because it's not technically part of that full cycle. But you do want to fill in that last point. So I think if you sort of work backwards, you can see that that point should be right on the x-axis. So there's that full, from 0 to pi, one full period worth of that curve. So this would be the final answer. You'd want to indicate that in some way. Okay. All right, so now we're going to go look at a tangent function. Okay, so as I'm sure you can tell, and I'm sure you know, the tan function is very different than sine and cosine. For one of the big reasons, you see you have these distinct little pieces. It's not a continuous function the way that sine and cosine are, primarily because of these things called asymptotes. So tangent is undefined starting at 90 or pi over 2 radians. Every 180 degrees or every pi radians you see another asymptote, so you keep getting these distinct little pieces. So what I find is helpful because of how strange tan looks on its graph is that when you're asked to graph a transformation of tangent, like y equals tan 2x, put it in your calculator alongside tan x and just sort of see the differences as the curves appear on your screen. So hopefully if you're following along and you've done that or you've done it before, you're seeing that because of this 2 that's sitting here, your frequency is increasing. It's doubling essentially. So you're going to have twice as many tangent curves from 0 to 2 pi as you did with regular y equals tan x. So what really ends up happening with your asymptotes is they're happening a lot more frequently. So you'd have one already at pi over 4, and then every pi over 2 you have another one. So they're never going to land in the same spots that they were before. Okay, so there's our asymptotes. That'll kind of guide our curves. And so now I'll start sketching in these curves. All of your x-intercepts are the same. So for example, this curve is still going to start at 0. It's just a little bit skinnier because its asymptote's coming much faster. And then you're actually adding on another curve in between here. Again, much skinnier because those asymptotes are so close together. Here we have our x-intercept there stays the same. Then you get another one in here. And then this last one, again, that x-intercept will stay, but that last black piece will have to be a bit skinnier to avoid that asymptote. So that would be the graph of y equals tan 2x.